Have you ever stopped to wonder how your computer really thinks? I mean, what's actually going on under the hood? Well, today, we're going to pull back the curtain and dive into the hidden languages that power literally every single device you own. It's a pretty fascinating world, so let's jump right in.
So let's start with a question. You type in the number 255. You see 3 digits you've known your entire life, right? 255. Simple. But what does your computer see? I can guarantee you it's not what you're picturing.
Yeah, it sees that. A string of 8 ones. This right here is binary, the native language of every machine on the planet. And this communication gap between how we see the world and how they do, that's exactly the problem we're going to solve today.
Here's the game plan. First, we'll tackle why this gap even exists. Then, we'll meet the 4 key number systems you need to know. After that, we'll learn the universal rules for translation, uncover a brilliant shortcut that programmers love, and finally, we'll see where this all pops up in the real world. Sound good? Let's do it.
All right, so first things first. Why can't computers just use our numbers? 1 through 10. It seems like it'd be so much simpler, right? Well, it all comes down to the simple fact that we're built completely differently.
See, we live in a base 10 world. We use 10 unique digits, 0 through 9. And, that's probably because we have 10 fingers. It's just intuitive for us. But computers? They're built from billions of tiny little switches. And for a switch, life is very simple. It's either on, which we call a 1, or it's off, which we call a 0. That's it. Their entire universe is built on this base 2 system, which we call binary.
So why should you care? Well, for one, we need a way to speak their language to tell them what to do. But as you saw with 255, binary numbers can get super long and clunky. That's why we came up with other systems to act as a kind of compact shorthand. And honestly, getting this is a total game changer if you're into programming, networking, or just want to understand how things really work.
Okay, so let's formally meet the main characters in our story. In the world of computing, there are really 4 key number systems that you'll bump into over and over again. First up is our home turf, decimal, or base 10. This is the system we all know and love. It's got 10 digits, 0 through 9, and we use it for everything. It's comfortable, it's familiar, no surprises here. Next, of course, is binary, or base 2. This is the computer's mother tongue. With a base of just 2, it only has 2 digits to work with, 0 and 1. It's incredibly simple, which makes it perfect for representing those on and off electrical states we were just talking about. Then we've got this one, octal, or base 8. It uses 8 digits, from 0 to 7. Now, you won't see this one quite as often, but it has some really specific, important jobs. For example, it's used in operating systems like Linux to set file permissions, who can read, write, or run a file. And finally, the real powerhouse of shorthand, hexadecmal, or base 16. Now, this is where it gets a little wild. To get 16 unique symbols, it uses our normal digits 0 through 9, and then it just borrows the letters A through F to represent the values 10 through 15. This is the one you'll see all over the place in modern programming. And check this out. This table really shows how it all fits together. Just look at the number 10. For us, it's 10. In binary, it's a 4-digit number, 1010. In octal, it's 12. And in hexadecimal, it's just the letter A. They are all the exact same quantity, just written in a different language. Okay, time for the fun part. How do we actually translate between these languages? Well, there are 2 fundamental methods that will work for any base. And trust me, they're way simpler than you might think. So to go from any base back to our familiar decimal system, we use something called positional expansion. It sounds fancy, but it's not. All it means is that each position in a number has a specific value. You just work from right to left, multiplying each digit by its position's value, and then add it all up. Like in this binary example, the positions are powers of 2. So the first spot is worth 1, the next is 2, then 4, 8, 16. You just add up the values where you see a 1. So 16 plus 8 plus 1 gives you 25. See? So what about going the other way, from our decimal system to another base? Well, for that, the magic trick is something called repeated division. All you have to do is keep dividing by the number of the base you're aiming for. Let's just watch it in action. If we want to convert 156 to binary, we keep dividing by 2 and just keep track of the remainder. So 156 divided by 2 is 78, with the remainder of 0. Then 78 by 2 is 39, remainder 0. You just keep doing that all the way down until the quotient is 0. Now here's the secret sauce. You take the remainders and read them from the bottom up. So 156 in decimal becomes 100111100 in binary. That's all there is to it.
Now, those two methods will get you through any conversion, but when you're moving between binary, octal, and hex, there's a much, much faster way. It's a little shortcut that pretty much every programmer uses.
The whole secret lies in this really beautiful mathematical relationship. Think about it. Octal is base 8, and 8 is just 2 to the power of 3. Hexadecimal is base 16, which is 2 to the power of 4. What that means is that one octal digit maps perfectly to a group of 3 binary digits, and one hex digit maps perfectly to a group of 4 binary digits. No crazy math required. It's just a direct translation.
So let's say you're a developer, and you're staring at this thing in a log file. Just a long, intimidating mess of ones and zeros. Trying to figure out what that number is, it's a total nightmare. But with this shortcut, it's going to become trivial.
So what's the trick? Since we want to go to hexadecimal, which is 2 to the power of 4, we just break the binary number into chunks of 4 digits, starting from the right side. We can even pad it with some zeros on the left to make that last group a full 4. So now, instead of one giant number, we've just got 3 small, manageable chunks.
And from here, we just translate each little chunk individually. 0011 is the number 3. 0110 is 6, and 1101 is 13, which in hex is the letter D. You slam them together, and that monstrous binary string becomes the clean, simple, easy-to-read hex value 36D. It's the exact same number, but wow, so much easier to work with.
So here it is. This is your mental flowchart for any number conversion you ever have to do. If base 10 is involved, either where you're starting or where you're going, use those universal rules, expansion or division. If you're just moving between members of the binary family, like binary, octal, or hex, always use the grouping shortcut. It's so much faster. And for any other weird conversion, just use base 10 as your middle step. Easy.
Okay, we've covered the why and the how, but where does this stuff actually show up in the wild? You might be surprised how often you've already seen it.
I mean, if you've ever built a web page, you've used hexadecimal for color codes. That pound sign, then 6 characters, that's hex. FF is the red value, 57 is green, 33 is blue. Every single device on your Wi-Fi network has a unique MAC address, all written in hex. Those Linux file permissions, that's octal. And whenever a developer is debugging code, they are staring at memory addresses, which are always shown in hex. It's not just to look cool. It makes their jobs infinitely easier.
So you see, these number systems aren't just some abstract math concept. They are, quite literally, the alphabet that our entire digital world is written in. Understanding them is like learning the basic grammar of technology itself. And once you know the grammar, you don't just have to use technology, you can start to understand it, create with it, and tell your own story.